Today we're going to talk about the complete optical modeling of a liquid crystal display. Breault Research has recently added capability in polarization devices and analysis. This enables modeling of a liquid crystal display all the way from the LED sources in the backlight, through the backlight unit, out the polarization optics of the front end. Results from these models can describe the extinction in the off state or the contrast level of the system. We can look at both directional and positional characteristics of the light in the viewer's space. Today, we will emphasize the directional pattern of light in viewer space for the off state of a vertically aligned liquid crystal device. We will also compare the full system result to a couple of simplified forms of the model. So to begin, let's take a look at the physical layout of the system. We're looking here at a small piece of the backlight unit. We've peeled the liquid crystal display polarization optics off of the front, and we're actually looking at the scattering dots, and they're actually not dots. They're tiny little dome-shaped scattering spots. Basically something that you could get by ablation or by punching and filling. So to zoom out a little bit, we start to see the pattern. It's not a regular grid, it's a randomized grid. And each of these two sections, between the red and the orange, has a slightly different spacing for the elements that are scattering. And that allows us to couple slightly different amounts of light out in these two zones. To look at the full system, I'll give you a better idea of what the full model entails. I'm going to peel a few layers off to show you what's inside. The key thing is, it's an edge-lit, roughly 26-inch or 660 millimeter diagonal HD format screen. This design is typically used for something like a computer display because it is edge-lit on one edge. The edge that is lit is this edge, which I'll call the left edge. And if we zoom in, we see I've put a few rays there just so that you can see that that is where it is lit from. And so now let's just take a look at the various layers that are here. On the top layer, I have a detector so that we capture all the rays that exit into the viewer space. Below that, I have, for the backlight design, a diffuser. It's in 3 layers because the diffusing surface is actually submerged inside a PET plastic layer. This is the actual top of the light guide. And the way the design was done is that the light guide was divided into 10 zones. We started the design by determining the dot density necessary to couple 10% of the light out in the first of the 10 zones. Then we added zones and continued across until we were coupling light out essentially evenly across the entire backlight design. This backlight has 65 LEDs on the left edge, and the goal was first to optimize on the one-dimensional output, and then we subdivided it into a 5x5 matrix and characterized the complete backlight behavior across the entire surface. We resulted in an irradiance output variation of less than 5% across the entire backlight when comparing zone to zone for the 5x5 zones. So now let's take a look at a little more of the detail of this entire design. I'm going to turn back on the entire design. So we have the detector, we have the top polarizer of the liquid crystal cell, we have the vertically aligned off-state liquid crystal material, we have the bottom polarizer, which of course is crossed with the top polarizer. We then have a DBEF simulation Basically, this is a polarizer which transmits one polarization and reflects the complementary polarization. We have a dummy layer that helps us keep track of what is on the polarized side of the interface and what is on the unpolarized side of the interface. And then we have a BEF layer. This BEF, if we zoom in, you'll see, you can just see the lines, is going across the backlight in the short dimension. And then I'll peel that further. This is a BEF that goes in the other direction. So it goes along the long dimension of the backlight. So we have two BEF layers and a DBEF for conditioning and recycling. Now let's zoom back out a bit and finish peeling it apart. And at this point, we're back to what I showed you before, the backlight design, which includes the diffuser and the actual bulk backlight itself. And we're only looking at two little pieces of the larger backlight here, basically 2 zones out of the 10, and we've narrowed it so that there are only 9 LEDs coupling into this section of the backlight. And that is what we're going to simulate for the first ever end-to-end modeling of a backlight unit. So the way we did this is we created the model similar to what I just showed you. It goes all the way across the backlight unit in the long dimension, but is only 9 of the 65 LEDs right in the center. We could do the whole thing, it simply takes longer. And the way I did this was I actually used ASAP Remote to do it. And while this is not an ASAP Remote demo, I want to show you just in motions how this is done. So I open ASAP Remote. I decide that I'm going to open a couple of sessions on a computer that I have permission to play with. I select the files, and I don't expect you to know this, but I select the files that I know are required to do my simulation. That's the actual run file, so I click it twice to make it so. And I set it into motion. I'm going to let it notify me when it's done. By the way, I have used only a few rays here so that you can just see how this works without having to wait hours. So when the sessions are started, I get a notice. I hit done, and they are off operating on solving the problem, each in their own way. Each has its own independent random number seed. And when it's done, we end up with a couple of files that we can combine to get the power of tracing twice as long on one computer, or we could use many more computers to trace even faster. And this is the essence of how this analysis was done. So what I'm going to show you now is the result of the extinction analysis in the output field as a function of direction for this vertically aligned cell on the backlight unit. That's what we have here. The result that you see on the screen is the result of running 4 sessions for a period of a couple of hours and then combining the results. I could have run for 4 times as long on a single computer, but I wanted to save time, as most of you do. So this is the result that I get from that first analysis. That analysis involved 2,000 rays per LED on 4 systems and took a couple of hours to run. Now I want to compare this result to a much simpler theoretical result that I think is very interesting. If I just take a cone of light and pass it through the liquid crystal stack without a backlight, I should get something that is comparable. Although this result that I'm showing you now tells us things about the system that that simple conical source and liquid crystal can't tell us. So let me just run this very quickly. It doesn't take very long. And here's the result, which is essentially a nearly theoretical result for the vertically aligned cell in just a cone of isotropic light. And so this is actually the ratio of the input radiant intensity to the output radiant intensity. So has a lot of the same characteristics, runs in a small fraction of the time, but we do see some hallmarks of the system. For instance, that this is the system model shows a not perfectly round output characteristic, while this does, because it started with just a simple cone of light. The backlight unit imposes some additional constraints on this. So this is one result, and this is a result that is very quick. The result of the simple conical source is a very quick way of optimizing the liquid crystal stack design. The idea is that we do the backlight optimization and the liquid crystal optimization, and perhaps even some things that sit between them, like the DBEF for recycling, get all of the pieces working, and then do a final system model. So now I want to show you a model that is somewhere between these. It's not quite theoretical, but it's taking a small section of the backlight, assuming that the light inside the backlight is well mixed, that the diffusers on the bottom side diffuse over a reasonably large solid angle, and in the end, that you get a lot of the system model characteristics in a small fraction of the time. So I have, with a very small number of rays, a good start on an estimate of the irradiance characteristic, and just to show you that this is very similar to the previous model, I'll peel back the side and show you. We have a little dot pattern that is causing light to be scattered out, and I just started with rays propagating upward through a large cone angle and propagating up, being recycled by the DBEF, and so on, being scattered back down, being reflected off a bottom reflector for cases where the rays came out the bottom, and ultimately everything comes up, or most of it comes up, everything ends up somewhere, and we get most of our light out the top. The recycling rate can be measured and so on, which is really a nice thing to be able to do with a simple section model like this. But enough about the model. It's the result that I really want to show. So here is this simple section backlight model compared to the full BLU or backlight unit with the liquid crystal stack on top. I put the same liquid crystal stack on top of the simplified sectional slab model, and we see something that looks remarkably similar. The thing that the backlight imparts that is somewhat unique is that we do have a sort of squared off shape for the envelope. And for that, you need a full system model. But we can do a lot of the design up front without having to spend the time or the effort on the full system model. So the upshot is, both are important, but we can do a lot of work in little bites and then do the big job as a final verification for the most part. And now I want to leave you with just one more interesting model. This is a simple, bare, vertically aligned dark state model. Now I want to show you, if I put in an ACA compensator for this vertically aligned cell, the kind of result we get. And I'm gonna get these two side by side, the two that are comparable, so that you can see what a difference it makes. So these are the two sort of theoretically based models that are based on just a cone of light going through the front end liquid crystal cell. So this is the simple cell, which is nothing but cross polarizers with a vertically aligned liquid crystal between them. So it's a halfway vertically aligned liquid crystal. And I'm going to put contours on it to show you the difference. The inner contour is the 10 to the minus fifth relative intensity point or contour. Now let's take a look at that here. So what you can see is that the 10 to the minus fifth contour has moved out considerably, and it's out at an angle that's roughly 23 or 24 degrees, whereas here it was just a few degrees. And in fact, we get contrast on the order of 1,000 to 1 out to something like 60 degrees. So that's a remarkable, well, not a remarkable result, a well-known result in literature, but a very simple device which, once figured out, does amazing things. In summary, we can do an end-to-end model. We can also do models of individual parts of the system and then put them together and do the full system model as a way of verifying that everything really works together the way we hoped. We can also add compensator design to our list of capabilities, and in fact could even do biaxial compensators. So we can do simple uniaxial compensator stacks as well as biaxial. And those are among the new capabilities that are useful in the display market.